Hello and welcome to this class of thermal analysis. In this lecture 31 of week 7, what we will just want to say is the thermal methods, and obviously those will be different thermal methods. That means, we will see the temperature effect on the sample or the analyte to change some certain properties, such that we can have some idea about the physical properties as well as chemical properties for our required analysis. So, it is a very useful technique. So, these thermal methods of analysis can be very useful. Why? Is the branch of analytical science basically people mostly use for the different types of material characterization, sample characterization, and also the quantitative analysis. So, where the properties of analytes, so any number of analytes you can handle and study as they change with temperature. If we find that some property can be changed with regard to the temperature, that means certain material is stable say up to 100 degrees centigrade, but it can change or it changes above 100 degrees centigrade. So, the reaction what is happening over there at that particular temperature or the transformed product we can see from this sort of analysis. So, one such example is thermogravimetric analysis or thermal gravimetric analysis we call, and is abbreviated as TGA. As we all know by now that what is a typical gravimetric analysis, and the most well known and well studied example of gravimetric analysis we all know, which is the corresponding nickel analysis. And as I told you earlier, nickel from any sample where this nickel is present as nickel bivalent cation, that can be taken away from nickel in the metallic state, such as from the steel sample or any other source such as the nickel containing mineral or ore. So, what we do there for simple gravimetric analysis is that we use dimethyl glyoxime as the corresponding chelating agent, and we get some rose red colored precipitate of NiDMgH whole 2, and this we get as a precipitate. We filter it out on a Gooch crucible, and then we dry it to take the weight of the dry PPT or the precipitate at around 120 degree centigrade. So, there comes the idea about the corresponding introduction of temperature. So, we are doing unknowingly we are doing the gravimetric analysis, that means by weight. Gravimetric means by weight we are doing some analysis, and this particular weight of the precipitate, which should be constant at this particular temperature. That means, it should not be hygroscopic and it should not be decomposed at this particular temperature. So, how do we know the precipitate, where we can dry the precipitate to take it exact formula of these? That means, the formula weight is also important. That means, we have to use the molecular weight, and molecular weight will also tell you that that much sample will have one atomic weight of your nickel. So, this constant weight of that corresponding precipitate will give us some idea that at 120 degree centigrade the precipitate is stable, will not decompose. So, we can find out the drying temperature. So, how do we find out the drying temperature? So, any other material, it can be your simple calcium carbonate or magnesium carbonate, and we want to get the dry sample of it such that we can take the exact weight of those materials. So, what we should concern about all these things is their thermal stability. So, this thermal stability is a very important thing for all these cases, and if we get this particular nickel DMG and if we try to heat it from room temperature, say 25 degree centigrade, and we keep on heating at 100 degree centigrade, at 200 degree centigrade, and this has been filtered out from aqueous medium. So, what was there? We have trapped water molecules inside this precipitate. The rose red colored precipitate has trapped water molecules. So, we have to remove these water molecules. So, initially when the precipitate was there, some adsorbed water is there and is not necessarily you can have some water of crystallizations, and in this particular case we do not have any water of crystallization present in this particular sample, but that also we should know whether the precipitate is a monohydrate or a dry hydrate or a trihydrate, where these water molecules are trapped inside the crystal lattice. So, if we can heat it up, so these adsorbed water molecules, so adsorbed water molecules will go out around this 120 degree centigrade. So, at this particular temperature we can heat it and then we can keep the precipitate in air oven, or we can do something that we heat it the air oven at this particular temperature and we keep the precipitate. That means, we know that when we dry the precipitate at this particular temperature, the trapped water molecule as the adsorbed water molecules will go out and will get the dry precipitate of these, because we must have the corresponding exact weight of the precipitate which is dry precipitate. So, at this particular point if we get that, so the thermal methods of analysis or the thermogravimetric analysis will tell us that if we use the property, that means if we can measure the weight change with the rise in temperature along this axis, say 25 to 100, 100 to 200 and beyond that, whether there will be any weight change or not. And if we find that at this particular range, which includes 120 degree centigrade, that there is no weight change even for the moisture content of the material, because when moisture is going out there will also be weight loss, because the water vapor will come out and this water vapor definitely have some weight. So, there will be some weight loss. So, at this particular temperature range, if we find that there is no such weight loss, so we can get that particular temperature as the drying temperature of that particular precipitate. So, any precipitate, n number of precipitate, we can have the corresponding drying temperature where we can dry the precipitate in air oven, which is applicable to say calcium carbonate, which is applicable to magnesium carbonate and many other samples, even good materials, plastics and all. So, that is why we have the TGA, the TG analysis we call also. The thermogravimetric analysis will be very much useful analysis, where we can have a typical experimental technique, because we will always think in such a way that when we talk in terms of the gravimetric analysis, we must take the weight of the precipitate. So, that means a balance is coming into the picture and we must have the corresponding analytical balance which can take the corresponding change in the weight or the mass precisely with the rise in temperature. So, what we get that in which the mass of the sample is measured as a function of sample temperature or time. Either you monitor this with the rise in sample temperature, the mass loss, or the Sometime we can also see that if we cool it in a reverse way, there can be some mass gain also. And if the heating rate of the furnace which is holding the sample over the balance is synchronized with that of our temperature rise, that means the rate of change of temperature with time is synchronized, we can also plot the thing against time instead of temperature. So, the sample or the analyte, we can heat it at a constant heating rate. That is very important, that why we should use a constant heating rate, so called the dynamic measurement. So, we have a constant heating rate of say 5 degrees centigrade per minute or 10 degrees centigrade per minute, or otherwise held at a constant temperature, that means isothermal measurement, when we can hold the sample as the constant temperature. So, we can monitor also the temperature rise in terms of the corresponding furnace temperature. So, what we get as the result? So, result definitely we will be getting as a plot. So, the results of a TGA measurements are usually displayed as a TGA curve. So, what we are monitoring? We are monitoring a property and the change of that property for any physical change or any chemical reaction. So, there will be some curve what we get, which mass or percent mass is plotted against the temperature and or time, because as I told just now that your temperature is synchronized with that of our time. So, we can get that thing. So, in other way we can also call this particular process as thermo-analytical method also. So, there are different thermo-analytical methods we can have, and we are just monitoring therefore the property of the sample, or sometime we can find also that we can monitor the temperature change also, because a temperature change can also happen with that of our happening the chemical reaction. So, if there is a typical chemical reaction, so we can find something that it is associated with certain temperature change. So, this particular analysis, so your TG analysis, thermogravimetric analysis we can have, and this particular one when we get it also we will see that one more methodology, which is if we plot this one, that means the TG plot. So, if the weight loss is like this, so there are these are all staircase like plots. So, this is the corresponding weight loss and this is the axis and this is the temperature axis, and this is the weight loss in percentage, because we standardize it with respect to the 100%. When we start this particular measurement, we find that we start from 100%, that means the weight of the sample, certain weight of the sample, say 15 milligram of the sample is taken and is heated as a 5 degree centigrade per minute rate. So, this particular one can be synchronized in that way that you have a 100% sample, 15 milligram sample will be your 100% sample, and then we find your percent weight loss, because that will immediately tell us what is going out from here and what is going out from here as moisture or any other gas. So, this particular methodology for this analysis is we get something which we call as a DTG curve. So, which is nothing but another form, that means a complementary presentation for the corresponding first derivative of the TGA curve with respect to temperature or time. So, if we get that, so this is the different lots, and if we just go for a corresponding first derivative plot, so the first derivative plot will be like this, and this is the corresponding TG trace and this will be the corresponding DTG trace. So, in this particular DTG, which we call as the differential or it is a derivative plot or a derivative plot for the thermogravimetric analysis. So, differential thermogravimetry or derivative thermogravimetry, where we monitor, basically this is the corresponding monitoring of rate of change of weight, rate of change of weight. So, what we require in case of TG, because we are talking about the measurement, that means the measuring of weight. So, we require a thermobalance. So, balance we all know, and most of these balances we call is as the typical analytical balances, and it can go for a very low weight change monitoring. And when it is associated with something where the thermal change, that means the sample where we keep the sample in a corresponding sample holder, that means the pan we consider, because the sample pan we all know, and that pan can be heated up, that means it is within a small furnace. So, if we heat the pan where you have the sample on that pan of the balance, so and we can have some mechanism for monitoring the corresponding change in that particular weight due to that particular reaction or any other physical change. So, we require thermobalance for TG as well as for DTG also we require the same thermobalance. So, how these particular thermobalances have been constructed, that all we see, because this first thermobalance which is introduced or used for experimental purpose is by Kotaro Honda in the year 1915, and later on most of these has been modified, and the modified form of all these thermobalances what was introduced by Kotaro Honda in 1915, still we use the different modified form of those balances, but the basic idea or the basic concept for measuring all these is very simple or very well known for all these. What it can do to, it can detect the weight change, or at the same time it can record the changes in mass of a substance which is your analyte, which is being heated or cooled. As I told you just now, that when you heat it, there will be a temperature loss. That means, this is the thing, if your moisture or water vapor is going out or some gaseous product is going out from the certain decomposition of the carbonate salts like calcium carbonate or magnesium carbonate, we will take specific example at what temperature that decomposition can take place. It can be any other organic solid also, that corresponding pyrolysis reaction we call, if it is organic solid, and organic compounds all we know that they can burn. So, the burning of any other organic material is also related to the product of these two. That means, when we burn any organic material or any food material or any pharmaceutical sample, we all know that the corresponding decomposition of carbohydrates also, they form the water as well as carbon dioxide. So, these mass changes related to any other sample, whether you have the trapped water molecule or the product of a particular reaction, even the corresponding carbonate salts, if we heat also, then we can have the carboxylates, organic carboxylates or inorganic carboxylate salts, the metal salts like copper acetate, iron acetate or nickel acetate, if we heat and if they decompose to give you carbon dioxide with the remaining or the leftover nickel oxide, all these things we can monitor very nicely. So, this is during heating something is going out, but when the same material is cooled in some environment, that means some environment of those things, that means those gaseous products which were going out during this heating process can also be trapped back by those materials. So, when it is cooled there will be wet gain, and that wet gain is due to the entrapment of carbon dioxide or your water molecule. So, we can have a very good idea about using these thermobalances with regard to the corresponding change in mass as a function of temperature or time, if it is synchronized for this temperature change. So, by doing so we get this curve. So, this particular curve we get, and that trace we plot. So, we must have a plotter, or nowadays the computer monitor is fine to measure all these things, and we will term those as the corresponding thermogram. So, those will be the thermogram. So, your Tg can give you the thermogram, your dTg can also give you the corresponding thermogram. So, this can also be known as, because we are talking something in terms of the corresponding decomposition in terms of temperature rise. So, it will be can also thermolysis curve, or if we consider that we are seeing something where the pyrolysis is taking place. So, it will be pyrolysis curve also, or thermo weighing, because ultimately what we are doing, we are seeing the temperature effect on the sample by weighing in a thermobalance. So, thermo weighing curve. So, all these things related to the very basic and the first two techniques we will go in detail while we do the sample wise, the Tg technique and the dTg technique. But we can have also the other processes. One such is the DTA process, which is known as its differential thermal analysis technique. Do not confuse it with your DTG technique, is a thermogravimetric G is there, but is typically the analysis, and in this particular the temperature difference we will be monitoring. So, the temperature difference we have to monitor between the sample and a non-reactive reference material or substance is again monitored as a function of temperature. So, there we bring something else, that means we bring some non-reactive reference substance. So, it can be simple very thermally stable material like alumina or any other oxide. So, with respect to that, so if we have the sample as well as that reference material, and within the same chamber, that means within the same furnace chamber, we try to heat it, but the temperature rise for one is different to that of the other, and we basically go for the corresponding delta value, that means the temperature difference. We try to monitor this as the delta T, and as a function of temperature or the control temperature of the two substances. So, how this the rise in temperature of the two substances are taking place, such that what we are trying to monitor, that heat is evolved. That means, the temperature for the sample will be more or will be absorbed, where the temperature of the sample would be less compared to your reference substance, because the reference substance will not undergo any such heat evolution or heat absorption. So, it will be basically a inert non-reactive reference material for our DTA analysis or differential thermal analysis, because the analysis is already included in the DTA term. So, what we get? We get basically from there is the measurement for delta T, where delta T is nothing but the temperature of the reference minus temperature of the sample. So, we have sample as well as your reference material is plotted versus the temperature of the sample. We plot it against the temperature of the sample, and now we need something which is little bit elaborate one, where we just do not use the very simple thermobalance for monitoring this thing. So, the DTA is a inbuilt process, or the instrument is also dedicated for your differential thermal analysis, and we thus we can have a typical DTA apparatus, and that DTA apparatus will be useful to monitor all these things, and we get a corresponding DTA curve or the DTA plot by the machine. So, after this DTA, what we can do? We can do something whose name is also related to DTA, but we bring something. We know that the thermal effect we can monitor by a calorimeter. So, calorimeter, when we bring into the picture of the DTA and we consider it as calorimetric DTA. So, it has a special name for that also, which is the technique will be known as DSC, and name will also tell you what is that. So, is differential scanning, because we are scanning all the time the temperature or the weight change, and this calorimetry. So, is the differential scanning calorimetry or DSC. So, DSC is also sometimes very much useful if we require sometime more information related to heat, not only the temperature. So, it is the difference in heat basically what is flowing into the sample or the reference substance, flowing into the sample or the reference substance. So, heat is flowing both to the sample as well as to the reference substance, and this particular change in that particular how much heat is gained by sample as well as the reference material, we can have the corresponding temperature rise and monitored as a function of temperature also the amount of heat. So, it is the amount of heat or delta H will be plotted against the temperature or time. So, is monitored as a function of temperature or time. So, now what we have? We have now the corresponding differential calorimeter, because the process is differential scanning calorimetry. The name immediately will tell you what is your apparatus to do that. It is the corresponding differential, which is slightly different from simple calorimeter, because we are seeing something where we try to monitor not only the age, but the delta H between the sample as well as the corresponding reference substance or the reference material. So, differential calorimeter. So, we monitor these things. So, in all these cases what we are discussing so far is the corresponding temperature effect or the heat effect we will see. Then we can introduce these two things to something where we all know that the analysis is incomplete if we do not talk about in terms of the corresponding titrations, simple acid base titrations and all these things, but we do not know when we go for some acid base titration what is the corresponding temperature change for the reaction vessel and what is the heat effect for the corresponding neutralization reaction. So, that we will see in our next class, that how we can differentiate these two, that of our standard titrations. Thank you very much.